Hello guys, so welcome now to lecture 2. We're gonna start this lecture by continuing our revision about what we have learned so far. I'm sorry, in the past in digital electronics in general and digital logic. So I want to confirm about again about the subtraction of using 2's complement, because there are some rules that we should keep in mind all the time. So basically, we said that one of the most important applications for using 2's complement is to use it in subtraction, because we basically convert the subtraction operation into an addition. So in principle, we can use the same circuit, we'll learn this in the future, to do both addition and subtraction. Okay. To understand now, what this circuit should give you, the result, you should understand some properties for the 2's complement. And I want to stress on two basic properties. The first one, the first property is the range. So what kind of, what range of numbers that we can represent with n bits. Okay, so if you have n bit number or n bits, okay, what is the range of values or numbers you can represent with? Okay, and now we have positive and negative numbers. They are signed numbers. That's why we are using 2's complement. Okay, and the rule is simple. So for n bits, the minimum number is 2 to the n minus 1, minus of course. Okay, and the maximum number is 2 to the n minus 1, minus 1. Let's have an example. For 4 bits or 3 bits, let's start by 3 bits. So the minimum is 2 to the 2, 3 minus 1 is 2. And this is negative, so this is minus 4. And the maximum is 2 to the 2 minus 1, which is 4 minus 1, which is 3. So we can represent from minus 4 to 3, right? And this is actually a cost that we pay to use 2's complement. Remember, if you have a 3-bit number, okay, then you can do from 0, 0, 0 until 1, 1, 1, 1. This is 0, by the way, in decimal, and this is 7. So you can represent from 0 to 7. So we can represent 8 different numbers. Here also we can represent 8 different numbers, but since we are including signed numbers with negative values, then the maximum range has reduced from 7 to only 3 in that case. So with 3 bits, we can represent minus 3, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3. Still 8 bits, but because including the signed number, we will use the maximum value from 7 to only 3. Okay, how about 4? We have here the 4. So for 4 bits, let's do it 4 bits. So the minimum is 2 to the 3 with minus, which is minus 8. And the maximum is 2 to the 3 minus 1, which is 8 minus 1, which is 7. Okay, so this is the first property. And let's take, from this example here and go forward to introduce the second important property that I want to introduce to you. So let's see how I can represent these numbers. So with 4 bits, I can represent minus 8, minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0. Then 1, 2, 3, 4, 5, 6, 7. Good. Let's look at the binary representation for those. And now we're going to represent the 2's complement of the negative number by its 2's complement. So let's start with the positive range. Here is the positive range from 7 to 1. So this is 7, this is 6, and so on until we reach 0. 0 is considered the positive number, that's not my problem now, but it's considered as a positive number. You may say it can be positive or negative, but they usually consider it as positive. Okay, for some reason we'll see now. So if we look here, we notice something, that all the most significant bits of these positive numbers are 0. This is the second property that I want to show you. That in that range, for 4 bits, for example, or 3 bits or whatever, when you are talking about signed numbers and you are considering positive numbers and the 2's complement for the negative number, you will find always that the positive number has 0 in its most significant bits. Let's now see negative numbers. Okay, here is the negative numbers. Okay, this is -8. How we can get this? Basically, 8 is 1, 0, 0, 0. To get the 2's complement, we invert each or flip each bit, and we add 1, 0, and carry 1, 0, carry 1, 0, carry 1. Then we get 1, 0, 0, 0. Okay, and here is -7 until we reach -1. Another notice here is that look at the most significant bit. They are all ones. So negative numbers has 1 at their most significant bit. So when you look at a binary number, and this is a signed number, you look first at the most significant bit. If it was 1, then you should take the 2's complement to reach back to its original value, and it will be minus something. So for example, if we look here at that number, which is a binary number, if we didn't consider any signed or unsigned, okay, this is 8, right? No, it's not, because we are considering a signed number and the most significant bit is 1. Then we must take the 2's complement to reach to its original value. For example, here, that number, which is -7, if we are not taking in mind this consideration of signed and unsigned, this is 9. But no, because if we say it's a signed number, then the most significant bit is 1. So we must take the 2's complement, and if we take the 2's complement, we will reach 7. 0, 1, 1, 1, 1. Okay, which is -7, of course, now, if we read it in decimal. Okay, so now what is the relation between this and our second topic in this lecture, which is subtraction operation? So if you are not considering such limit, okay, on the range, then you might get an overflow in your subtraction operation. So let's have an example and see the problem by our eyes. So let's add up -15 and -3. Okay, one may say, okay, 15 is 4 bits. Okay, so 15 is 4 bits. Let's write it in its primitive way or unsigned way, which is 4 ones, which is wrong now, because we know that 4 ones will not be enough to represent -15. And -3, and this is 15. So we take the 2's complement. It will be 0, 0, 0, 0. We add 1. It will be 0, 0, 0, 1. And this is wrong, because we know that 4 bits is not enough to represent -15. And the 3 is 0, 0, 1, 1. Take the 2's complement. I'm sorry, this is 2's. 2 apostrophe S. Okay, so it will gonna be a 1100, then we add 1, it will be 1101. Then we add them 0001, 1101, 0 carry 1, 1, 1, 1. Okay, we know that the result should be negative. So we're gonna take the 2's complement of that guy. So 0001. We add another 1. So 0, 1. That's of course 2 or minus 2 now, because we know the out is it should be minus 18. So the output should be minus 18. And this is not minus 18. This is minus 2, because what is called overflow has happened here. Okay, and the range of bits that we started with is not enough to represent minus 18. Okay, so how are we gonna fix this problem? We fix it first by choosing the suitable number of bits to represent 15. Our basic problem here is was 15, by the way. Okay, good. So we said that for 4 bits, which what we assumed for such example, can represent from 2 to the 4 minus 1 in minus 2, 2 to the 4 minus 1 minus 1. This is minus 8. This is 7. So basically, minus 15 cannot be represented by 4 bits. How about 5 bits? Let's check this. 5 bits. So we can represent 2 to the power 5 minus 1. 2 to the power 5 minus 1 minus 1. This is 2 to the 4, which is minus 16. And this is 2 to the 4 minus, which is 15. So we can represent minus 15 using 5 bits. Because with 5 bits, I can represent minus 16, minus 15, minus 14 until we reach 0, then 1, 2 until we reach 50. This is the range that, that can cover, our 15. So the minimum number of bits that we can use for such subtraction, which is minus 15 minus 3, is 5 bits. So let's do it. Let's redo it with 5 bits, and let's see what's gonna happen. So now 15 and 3, we're gonna represent 15 with 5 bits. So 0, 1, 1, 1, 1. And 3 is 0, 0, 0, 1, 1. We take the 2's complement of both. So 2's complement here is 1, 0, 0, 0, 0. We add 1. So it's gonna be 1, 0, 0, 1. So this is minus 15. And look now at the least significant bit. It's 1. And we know that, when you write signed numbers in 2's complement form, the most significant bit should be 1 or must be 1. So if we look back here, before we continue, so here is minus 15 with the wrong representation of 4 bits, okay? And the most significant bit is 0, which is wrong. It should be 1, which represents negative. That's why we have a problem. Good. How about 3? Let's take the 2's complement. So this will be 1, 1, 1, 0, 0. We add 1. So 1, 1, 1, 0, 1. This is minus 3. Now let's do the addition. 1 plus 1 is 0, and we have a carry of 1. This will be 1. This will be 1. This will be 1. This will be 1 plus 1 is 0, and we have a carry of 1. So this will give us 1. Okay. Now we know that this should be a minus number. Okay, so we take the 2's complement of that number. So if we take the 2's complement, we first, flip each digit. So this will be 0, 1, 0, 0, 0, 1. Then we add 1. 1 plus 1 is 0, and we have a 1, 1, 0, 0, 1. Okay. And if we check this in decimal, this is 19. This is 18, because this is 2 to the power 0, which is 1, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4. And 16 plus 2 is 18. So the output is minus 18. When we read it, we write it in, like a positive number, but when we read it, we know it's minus 18. Okay, and of course this is minus 18 into this. This is the 2. This is minus 18, in its 2's complement format. Okay, the book will say to you, discard the carry bit, which is this bit. Yes, we can discard it because when we do the 2's complement, we will flip it to 0. So it has no value because it will be on the left here. So it has no value. So you can just consider it on a paper and a pen. If you are designing, you can just ignore this wire. You can even discard this wire and not basically design it, as we will see later when we design the others. Okay, but anyways, it will be converted to 0. This carry here that I talked about last lecture and the lecture before, you can just flip it to 0 and it will have no problem at all, or you can discard it from the beginning. Okay, guys. So this is basically a quick review about 2's complement. It's two basic properties that we need when we do subtractions, and we see that overflow can happen if you didn't respect the range that each number of bits can represent 4 signed numbers. Okay, so see you in the next video.